In this video, we want to find the volume of the solid generated by revolving the region bounded by y equal 1 over x squared, the line y equals 0, the line x equal to 1, the line x equal to 4. And for part A, we want to find the volume when this region is revolved around the x-axis, then the y-axis, and then the line x equal to 4. Now the graph, or the function rather, y equal 1 over x squared, numerator is always positive, positive 1. The denominator is square, so you know the graph is above the x-axis. So you can plot a few points, or use your graphing calculator, you get just a rough sketch. That's all you need. So the region we're looking at here, and again, it's in the first quadrant. The line x equal to 1, x equal to 4, line y equal to 0, and then of course the function y equal to 1 over x squared. So basically we're looking at this region right there. So let's look at a quick review here. There's several methods you could use. In some cases, either one will work. Sometimes it's more convenient to use one rather than the other. So the disk method, we looked at some other examples before, uses perpendicular rectangles. So if the axis of revolution is horizontal, in other words, if you're revolving around, say, the x-axis or a horizontal line, y equal 4, you're going to use perpendicular rectangles, and you'll be integrating with respect to x. R of x will be the radius that you'll be forming. So r is the outer radius. Let's look at it here. Let's say you have this region here, and this is your representative strip. So you rotate it. It's going to form a disk. It's going to have a hole. See the space here. So this is the axis of revolution here. And from here to the representative strip here, so from here to here, that's your R. That's the outer radius. Again, the distance from the axis of revolution. This could be just a regular line, or it could be the x-axis. And then the smaller radius is R. And these will be in terms of x. This will be some function, and the distance from the base of this to there will be r. That's the outer radius. And then from here to here, whatever this is here, this distance here, that's going to be the inner radius. Rotate it, and it's going to form a disk or a cylinder with a hole. Now, if it turns out, let's say you're rotating something like this, you form your rectangular strip here, you rotate that about this axis, or this could be a line over here somewhere, horizontal here. And this would only have capital R, one radius, because since it touches the axis here, small r would equal to 0. So you wouldn't have it. So in this formula here, if the region coincides, the base of the region coincides with the axis, then r is going to be 0. So this is gone. So you just take the outer radius, square it, and this usually will be, again, a function of x. Usually it's going to be that function that's given. And of course, you're going to have your definite integral. So the first thing you want to do, of course, is sketch the graph of the region that's given, determine your limits of integration, determine your radius, square it, and again, if it's you're rotating about a horizontal line like the x-axis, or y equal to 3, y equal to 4, and you're integrating with respect to x. So determine what's the variable of integration. If it's x, then you want this function in terms of x. If it's y, for example, over here, this one, of course, is dx here. But if you're rotating, say, if your disk was perpendicular to the y-axis, so your region was over here somewhere, this would be dy. Anything in here, of course, your limits of integration will be along the x-axis here, the y-axis, and you would set up your function f of y. So this is what it would look like if the axis of revolution is horizontal. Everything in terms of x And of course, the pi r squared and then the dx comes from the fact that that's the formula for the volume of a cylinder. Pi times the radius squared, pi r squared, h, height. In this case, we're using dx, or if you're doing a rotation about the y-axis, then this would be dy, and you have this formula. The axis of revolution is vertical, and the volume is given by this. Pi, cd, these would be limits of integration along the y-axis. Same thing again, if the base of that region is on the y-axis, then the r will be 0, and you're just going to have the r squared. Otherwise, you just put in whatever you have, integrate, and then evaluate. Now, in some cases, you might have the rectangle, the representative rectangle, it might be parallel to the axis. So this one states, this is called the shell method. Now over here, if r is 0 here, in either one of these forms, then that's just called the disk method. If r is not 0, your disk is going to have a hold, and that's going to they'll call that the washer method. Now if the rectangles that you form, representative rectangle is parallel to the axis of revolution, or if the axis of revolution is horizontal, then the volume of the solid of revolution is given by this formula. Again, having to do with the volume of a cylindrical shell, 2 pi cd ry hy dy. And if the axis of revolution is vertical, then the volume of the solid is given by this formula, 2 pi integral from a to b rx h of x dx. So if you're using the shell method, the rectangle that you create to set up the integral is going to be parallel to the axis of revolution. Whereas in the disk method, the rectangle is going to be perpendicular to the axis of revolution, whether it's horizontal or vertical. The disk, or the rectangle rather, will be perpendicular to the axis. Now, for this one over here, for this formula here, what you have in terms of dy, here's what we have. dy is going to give you the width of the rectangle, also called the thickness of the shell. Creates the shell. Hy is the length of the rectangle, or the height of the shell. And ry is the radius of the shell, which is the same thing as distance between the axes of revolution and the center of the rectangle. And this is what it looks like if you have a axis of revolution that's horizontal and you're using the shell method. The rectangle has to be parallel. This width here is the thickness, will be denoted by dy, and of course that means the integration will be with respect to y. Limits of integration from c to d, and then hy is going to be the length of the rectangle or the height of the shell. So for this one here then, for the first one I'm going to use the disk method. So I look at my region. Like I said, the region is going to be in here, contained below this graph and in between the two lines, x equal 1, x equal 4, and of course the x-axis, which has equation y equal to 0. So the volume will be given by, okay, so the integral goes from 1 to 4. It's just the line x equal 1, x equal 4, so this will be 1 to 4. And it's pi r squared, but I put the pi out here. And I'm going to draw my representative rectangle here. This method and the axis of revolution is the x-axis, so it's horizontal, so I want my disk or rectangle to be perpendicular. And remember, when you integrate, it's really taking an infinite number of rectangles and computing the volume when you rotate each one of them. That's what the integral does from 1 to 4. So this width here is dx, that's going to be over here at the end. And then the radius will be, again, from the distance from the axis of revolution to the curve. So it's going to vary as you go through here. So what is that radius? That was r of y. And in our case, that would be 1 over x squared. So the radius here is 1 over x squared. So this was capital R in the formula that we looked at, and it was r of x, and it was squared, and then it was dx. Notice r is 0 in this case, small r for the inner radius. So this is the outer radius. The inner radius is 0. This is what you have. So this is from 1 to 4. Then let's square this out here. It'll give me 1 over x to the 4th, and then to make it easier to integrate, bring this up to the numerator, make it x to the negative 4 dx. Now this region had been up here somewhere, and you'd have to rotate it. Then you'd have an inner radius, but in this case it's 0. And then we just integrate here. This is 1 to 4 here. So add 1 there, we get x to the negative 3, and divide by negative 3. And then limits of integration go from 1 to 4. And we plug in the 4 here. That's 4 to the negative 3. Bring it downstairs. That's 4 to the 3rd times 64. So it'll give us, this will give us negative 1 over 192. Again, put a 4 here. Take it downstairs. That'd be 4 to the 3rd is 64 times the negative 3 here. And you have a 1 up there, so it'll be minus 1 over 192. And then it's reiterated 1. So this would be 1 there to the negative 3, still 1. And then you have them, so you're subtracting that. So that's plus 1/3. On your common denominator here, multiply here by 64 and 64. So it'll be 64 over 192, and then a negative 1 gives you 63 over 192. And that's going to be times pi here. You bring it up here now, then just reduce it, divide by 3, so we get 21 pi over 64. And you can approximate this using your calculator to 2 or 3 decimal places. I'm going to leave it like this. So we got 21 pi over 64. Now for the next one, you want to rotate this same region about the y-axis. So that means our rectangular strip would have to be perpendicular. I'd have to have my limits of integration along the y-axis. So what I'm going to do now on this one, I think it would be more convenient. I think it'll be easier to use the shell method. So for my shell method, the rectangle has to be parallel to the axis of revolution. So I still have it right there, but now it's going to rotate around the y-axis. So my volume here, V then would equal to, for the other formula, this is 2 pi. Goes in with a shell. Notice the rectangle width is right here. So that means we're going to integrate with respect to x. So we're going to still use the same limits of integration here. I'll leave that 2 pi out here. It was 2 pi, and then limits of integration here, it's the same. Because we're using dx here. So this will be from 1 to 4. And the radius then would be, again, the distance from the axis of revolution to the center. So from here to here, that's x, and we're integrating with respect to x, so that's okay. This will be x here. And then the height, h in the formula, is this right here, or the length, if you want, of the strip, would be the function, which is 1 over x. This is 1 over x squared. And the thickness would be dx. If it was the other way around, it would be dy. So say this is going to cancel here. We have x and 1 over x. So this is just going to give me x, 1 over x squared. This will simplify to 1 over x. So it's 1 over x dx, so this just gives me 2 pi. This leads to the integral involving ln of absolute x. We did it with positive numbers here, so I just leave it like that. And this is going to be evaluated from 1 to 4. Evaluated at 4 will give us 2 pi ln of 4. And then subtract the value at 1. Put a 1 there. ln of 1 is 0 times 2 pi. That's still going to be 0. So the answer comes out to the volume of this solid revolution is 2 pi ln of 4. Now we can just remove this. Like I said, if it calls for an approximation, you can use your calculator. But that's the answer for that one. Now for the next one, C, we want to rotate around the line x equal to 4. Again, I think this will work out better if I use the shell method here. So let me put my rectangular strip here. It's going to be the volume using the shell method. Notice, because the rectangle is parallel to the axis of revolution, which is x equals 4, the width here is dx. I'm integrating with respect to x again, so the function will be in terms of, sometimes you have to change this to y when it's the other way around, but in this case, the limits of integration are still going to be the same from 1 to 4. I have the 2 pi out here. So what do I need here? I need the radius. So the radius then is going to be the distance from the axes to the center here. So let me just do this from here, that distance. If it's 4 there, and then here would be x. So this distance here would be x. So I want the distance from this point to the axis of revolution. So it to be 4 minus x. So the radius r of x is 4 minus 4. And then the height of the rectangle, anywhere you put it, it's always going to be this distance here. Put the rectangular strip over here or over here. The height will be actually just the function. Goes for the axes, the x-axis in this case, to the curve. So it's going to be 1 over x squared. And then it's dx. And then it's just a matter of integrating this. It's equal to, and this is 2 pi here. This will be 2 pi then. 1 to 4. So let's multiply here. It'll be 4. X to the negative 2 minus x times 1 over x squared. Simplify that. Reduces to minus 1 over x. Integrating with respect to x. Let's rewrite this one here. 4 over x. This is a positive here. 4 over x squared. Take it to the top though. 6 to the negative 2. And then we just integrate here. 4x to the negative 2, add a 1 to that one, we get negative 1 and then divide. So this will give us a negative 4. Give me x to the negative 1. Add a 1 there, negative 1, and then divide the 4 by negative 1, I get negative 4 x to negative 1. And then we look at minus 1 over x dx, that's the one for ln of x, so this will be ln minus ln of x. And then we just evaluate from 1 to 4. So let me put it over here. So this would be 2 pi. And I'm evaluating this thing at 4. So put a 4 where the x is. Put a 4 here. 4 to the negative 1 is 1 over 4 times a negative 4. That'll give us a negative 1. And then it's minus ln of 4. Then it's a minus. Okay, so we again evaluated the upper limit. 4 there to negative 1 gives you 1 over 4 times negative 4, so it's negative 1. Then a 4 there, minus ln. It's minus. I put a 1. So it'd be minus 4. Put a 1 here, that's 1 to the negative 1 is 1, so this would be a minus 4. And then put a 1 there where the x is. It'd be minus ln of 1. This is 0 here. So I get 2 pi here. 0 here, and then a minus here's a plus 4. And a minus 1 is 3. And then I got minus ln of 4. So the final answer for this one, the exact answer, is 2 pi multiplied by, brackets there, 3 minus ln of 4, 2 pi multiplied by, in parentheses or brackets, 3 minus ln of 4. And of course, again, you can give an approximation if they ask for it. I'm going to give the exact answer. So I'm going to leave it like this. Thanks for watching. We'll see you next time.